All right, we're going to take a look at our next lesson, 6.5, Optimization Problems Part 2. And in particular, we're going to be looking at exploring solutions. Let me get everything set up for us here. The objective of this lesson is to take the feasible region of the system of inequalities that we've created and begin to explore the region and just try to decide, okay, where are the minimum values? Where are the maximum values likely to be? Last class, as I mentioned, you learned how to create a model for optimization problems. So you knew how to set it up and get it ready and to graph these things. And what we want to take a look at is within the feasible regions, let's explore some of the values to see if you can get a sense of where your maximum values are going to be and where your minimum values are going to be. We're going to do this through the use of a question. So just familiarize yourself with this by stopping the video and reading it so that you have some idea what it's talking about. And then we'll go through the steps together. Step number 1, define the variables that affect the quantity to be optimized and state its restrictions. So you read through the text and you always look towards the last part and you realize that it asks for the greatest profit. So the quantity that they want you to optimize is profit. So then we need to go back into the question and say, okay, well, what are the variables that will affect the profit? And we realize it's going to be the paint jobs on cars and the paint jobs on trucks. And so we establish that those are our variables. And we stop and consider, well, these are probably most naturally whole numbers. Step number 2, identify the quantity to be optimized. Well, you've already done that. And then you realize that it's the profit. So profit's going to be optimized. So that when you get to the third step and they ask you to create the objective function, you're all set. You know that you've got to describe how you're going to find the profit. So 250 times the number of cars plus 400 times the number of trucks. And that will give you the profit that you've earned in this particular scenario. Okay, the next step, once you have all these other things in place, you're going to be setting up your constraints using a set of linear inequalities. And there are a couple buried in the text of the question. Because of the size of the workshop, the company can paint a maximum of 8 and a maximum of 5, and that the total output for the shop cannot exceed 10 vehicles in one day. So each one of those 3 facts can be expressed as an inequality. X is less than or equal to 8, Y is less than or equal to 5, and X plus Y is less than or equal to 10. Okay, next step, graph them. And here you have a graph that's kind of describing this. You can see here's X equal to 8 and all the values that are smaller than that. Here's Y is equal to 5, and so all the values that are smaller than 5. And here's your diagonal line, X plus Y equals 10. You see the X-intercept and the Y-intercept are both at 10. So you've got a diagonal line and you're going to show underneath it. So the overlapping region is the area that we're going to explore. This is what we call the feasible region. It's the region where you're going to be looking for the maximum value for the profit. So what we're going to do now is just take a look at some specific points, because remember, these are literally whole points, whole numbers, and we're going to look for the patterns of what happens. So for instance, let's take a look at what happens when we start on the left and go to the right. So we start with 1, 1, and we go to 7, 1. What we're going to do is take those numbers and put them into our profit formula. If I put a 1 in here and here, I get 650. So the profit for this point is 650. If I do 7, 1, with this one, I'm going to have 250 times 7, which is 1750. And then I'll have 400 times 1. So 1750 plus 400, we're looking at 2150 or so. So definitely it has grown bigger. So as we move from the left to the right in the points on our graph, we are getting to larger numbers. Let's try points going from the bottom to the top. So I go from 1, 1, which I know already is 650. And let's see what would happen if I did 1 and 4. Well, 1 is 250. 400 times 4 is 1600. So I'm looking at 1850. So sure enough, it's gone from 650 to 1850. So as it goes from the bottom to the top, it also gets larger. So what happens as you move the value of the profit, as you move from left to right? It gets bigger. What happens to the value of the profit as you move from the bottom to the top? It gets bigger. So that gives us a chance to be able to assume that the minimum values are going to be down and to the left. The maximum values are going to be up and to the right. So when it comes to trying to sort these out, and we're trying to play around with them, especially in the examples you do in your homework, make sure you always check the furthest up and the point furthest to the right. You just sort of play around with all of those to find the maximum values. And for the minimum values, sorry, this one should have said minimum here. It should be the values a couple points down and to the left so that you can play around with it a little bit. Just a couple more hints as you go into it. Important things to remember. Basically, the best solutions to the objective function are actually represented by the vertices of the feasible region. We'll be doing this a lot when we do our next lesson and try to sort out what our answers actually are. But it turns out the vertices are your best. And if for some reason your actual vertex is not in your solution because of some of the constraints on it, your answers will be nearby. And always you can verify your solutions to make sure it satisfies every constraint by substituting them in and checking to make sure that they fit within the linear inequality if you're worried about it, especially when you start moving around with points that are nearby. Okay, there you have it, exploring the feasible region of a system of linear inequalities. Good luck with your homework, everybody.